Hello everyone, we are still talking about the shortest path problem. We have discussed the digester algorithm for the graphs with non-negative um, weights. So now we wanted to see that what would happen if the graph has negative edges. So the digester algorithm, let's see that how the digester algorithm is going to work if the graph has negative weights. You can see that if I run the digester algorithm over this graph starting from S, it's going to actually find T with the cost 1 and says that the cost of visiting T is going to be 1. Although it is clear that if I visit T through this path, the cost is going to be -1. So the digester algorithm in this case is going to fail. The reason is that digester algorithm works, digester algorithm is a greedy algorithm, and the whole idea of the optimality of the greedy strategy for the digester algorithm is that the cost of all edges are non-negative. So if you have already visited a node, it is not possible to find some other path using more number of actually edges later that give you less cost, because the cost of all the edges are going to be non-negative, right? So if you are going to find some other path, definitely you are visiting some more edges with some non-negative cost. But if the edges can be negative, for example, in this case, if you go through this path, you can see that because of the negative cost of some of the edges, the shortest path is going to be different. The greedy algorithm, that greedy strategy of the digester algorithm, is not going to give me the optimal answer anymore. So what is the answer? What is the solution to solve this? The thing is, if we have negative weights in our graph, assuming there is no non-negative cycle, we have to check all the possible paths to find the shortest path. The greedy algorithm is not going to work, so you have to basically check all the possible paths from S to every node to find the optimal answer between S and that node, the shortest path between S and each node. Why I'm saying there shouldn't be any negative cycle? Basically, the idea is that if there is a negative cycle from the node S to some, for example, node T, if there is some negative cycle, the cost is smaller than 0. So you can simply just actually argue that I am going to go through this cycle again and again and again and again. You can actually go for forever, so the cost is going to be -infinity, and basically there is no shortest path over a graph that has a negative cycle. You cannot actually define the shortest path in that case, right? So completely our assumption is that there is no negative cycle in the graph. Otherwise, the shortest path problem cannot be actually solved. So if the shortest path problem, if the graph algorithm that we have doesn't have a negative cycle, we can still put some constraint over the shortest paths between then every node, the node S and every node T in the graph. We know that because there is no negative cycle, if you are going to find the shortest path from the node S to node T, it's not possible to have a cycle. The reason is that because the cost of the cycle is positive, definitely if you remove it from the path, you are going to get a better, the shorter cost, right? The lower cost, the shorter distance. So it's not possible to have a cycle. And because it's not possible to have a cycle, the maximum number of nodes that you can have in between, it is going to be n minus 2. And so the total number of edges is going to be at most n minus 1 edge. Okay, so this constraint is going to help me to define the dynamic programming algorithm, some dynamic programming, some recursive relationship to find the shortest path for the single source shortest path problem. So be careful here. Again, the thing is we have a graph and we have a node S in the graph that we wanted to find the shortest path starting from S to all other nodes in the graph. Okay, and there it is possible to have negative weights, but it is not possible to have a negative cycle. So in this dynamic programming algorithm, I'm going to basically find the that recursive relationship, and based on that define the shortest, define the subproblems. The recursive relationship that I wanted to write is going to be based on the number of edges, actually. Okay, so I am going to define D of V and I to be the shortest path from S to V, from the node S to each node V, the shortest path from the node S to V using at most I number of edges. Okay, so be careful here. It actually tells me that at most I number of edges. It doesn't mean that you necessarily need to use exactly I edges. You might actually use just one edge or I edges. Whatever is going to be actually better. So, but it just actually puts some constraint over the number of edges. So for the base case, I would define D of V and 0 for all the nodes except S to be infinite. And it is clear, if you are going to find the shortest path from S to any node V without any edge, without 0 edges, definitely the cost is going to be infinite. It's not possible to find any path from S to any other node. Then I'm going to find the recursive relationship for D of V and I for any value of I and for any node V. So it is going to actually give me two options. The problem is very similar. The pattern that I'm following here in this case for this dynamic programming algorithm is very similar to the case of the knapsack problem that we were actually just thinking about maximum this number of items. Okay, here we are actually just putting that if we are using at most I number of edges. So for the calculating the cost of D of V and I at most I number of edges, you might actually just say that, okay, I is the last edge that I am going to use. Okay, the number of edges, it's not talking about the path, it's just talking about the cost. Okay, so either I am going to use the ith edge or not. If I don't use the ith edge, it's going to be D of V and I minus 1, right? The cost, the shortest path from S to V using at most I minus 1 edge. I'm not going to use I edges, just I'm going to use I minus 1 edges. Okay, so it can be this one, or I'm going to use the ith edge. How I'm going to use it? You would actually say that I'm going to find the shortest path from S to V, right? So that the last edge that I am going to use should be some edge that actually going to V, right? So for all those edges, incoming edges to V, you would check that what is the distance from S to A with I minus 1 number of edges. What is this path? What is the shortest path here? Plus the cost of going from A to V. Okay, so you are checking this for all the edges, basically checking that one, and also, for example, D of B and I minus 1 edges. What is the shortest path from S to B using only I minus, at most I minus 1 edges, plus the cost of B and V. Also, you actually just calculate it for all those edges, all those nodes that have an edge to V. You compare all of them and get the minimum between all of these ones, and also actually this case that you don't use the ith edge. So basically whatever is the previous value, the cost of reaching to V from S using I minus 1 edge, you compare it with the minimum of all those nodes like ABC, for example, here, that the cost of the node the cost of reaching from S to U and I minus 1 for all those nodes that have an edge to the node V. And here is actually just the cost of that final edge. So that's it. This is the dynamic programming. This is the recursive relationship to define D of V. What I can write is just I can write it as a minimum of between, this is the base case and this is the full recursive relationship. And you can see that we put the constraint over the number of edges. We know that because there is no negative cycle between from S to any node, you might at most use n minus 1 number of edges if you have n vertices. So D of V and n minus 1 is going to give me the shortest path between S and any node in the graph. So this is the full algorithm. This part actually shows the the basic of the recursion. You just define D of U and 0 equal to infinity for all the nodes. Just change it for S to 0 because it is clear that the cost of visiting S from S is 0. You don't need to use any basically any other edge. And as always in the BFS, in the digester algorithm, we always actually keep that array of the parent. Basically just this array of parent tells me at the end we can actually find the shortest path, the actual shortest path, by following the edges in the parent array. Otherwise it's not possible to find the shortest path, finding the actual path. So I have a loop that iterates over the value of I from 1 to n minus 1, using at most 1 edge, using at most 2 edge, using at most 3 edge, until using at most n minus 1 edge. So in total, the algorithm is going to have a loop that iterates from 1 to n minus 1. And for each node, so basically in using these two loops, you are going to calculate D of V and I for all the vertices and all the number of edges between 1 and n, or between 1 and n minus 1. And so for each case, this is the loop that calculates this part for all those nodes that have a weight, an edge to V for all the nodes U that has an edge to this node V. Okay, you just calculate and compare this cost with the cost of D of V and I. I have actually initialized it with D of V and I minus 1. So in this way, at the end, you would calculate the minimum between D of V and I minus 1 and with all these different cases. It's just actually implementation of the recursive relationship that we have before. And whenever you find a better cost, you update the parent for that node as well, that in the array parent. So what is the time complexity for this algorithm? This is a dynamic programming algorithm. I think this is quite clear that you have this loop is going to iterate n times. This loop is going to iterate again n times for every vertex, right? And but inside this one, we are actually just checking O of degree of V, right? Basically in degree of V. So it's going to be based on the number of edges. So in total, these two loops in total is going to iterate O of m times, but the outer loop is going to iterate O of n. So in total, this is going to be, this multiplies to the number of iterations of the outer loop. So the total time complexity of Bellman-Ford algorithm is going to be O of mn or nm. Okay, because this part is going to be O of m in total, because you are checking all the edges here basically, and the cost of the outer loop is going to iterate n times, so n will be multiplied by m, the cost is O of nm. So let's just actually execute the Bellman-Ford algorithm over this example here. As you can see, this table is basically showing that table of D of V and I. So the first dimension is for the vertices, and the second dimension is for the number of edges. It shows that 0 number of edges, at most 1 number of edges, at most 2 number of edges, and so on. And I'm here actually showing that parent array as well, that you have to keep it, otherwise it's not possible to find the shortest path at the end. I have actually covered all the steps of the algorithm, but I'm going to just do a couple of those steps and leave the rest of it for yourself to go over it. So at the very first, what we did was initialized everything except the S, the starting point, to be infinite for I equal to 0. So everything here is infinite, and the parent of this one is null. Okay, so this here shows the first step before basically this part. Okay, so then we are going to go through this loop when I is equal to 1, or let's use a different color. Okay, when I is equal to 1, it actually tells me that I am going to calculate D of V and 1. So intuitively, this will be just all those nodes that have one edge from S. But I'm going to just stick to the algorithm and show you that how the algorithm works, that if you just run the algorithm, just iterate over the algorithm, it just gives you the answer, right? So for each edge, you would define d of v to be d of v and I minus 1. Then for each edge you are just checking all those, for each node you are just checking all those nodes that have an edge to this node. So for S, this is going to be 0, of course, this is not going to change. For A, this is going to be the cost of A using at most one edge is going to be the minimum of the cost of A and 0, which is infinite, right? And the cost of all those edges, all those nodes that have an edge, incoming edge to A. So for example, B, F, and S, you can see that the cost, for example, for B, from B to A, the weight is 1, but the cost of B and 0 is infinite, right? Again, the cost of F and 0 is infinite. So they are not going to give me the answer, but the cost of S and 0 is 0, right? Plus 10, this is going to be the minimum cost for A. So the minimum cost for A and 1 is going to be 1. B and 1, you can see that all those edges, this is not very clear, but anyway, this is the only incoming edge to B is coming from E, okay? But the cost of D of E and 0 is already infinite. So the cost of B is not going to change, it is going to be infinite. The cost of C is going to be infinite. The cost of D is going to be infinite. The cost of E is going to be infinite. The cost of F is going to be infinite. Only the cost of G is going to change as well. The cost of G is going to be the cost of S and 0 plus that edge from S to G. So this is going to be 8. So the parent for G is S, the parent for A is going to be S. So we are done with filling the second column of the table. Okay, you can see that this part and this part have been updated. Now this the second iteration. You are going to calculate the cost of course, S is not going to change, it's going to be 0. The cost of A and using 2 edges. So for A using 2 edges, basically it's just like, again, you only have 3 incoming edges. You are checking for all of them. For F, the cost of F and 1 is already infinite, so it's not going to update anything for me. The cost of B and 1, this is infinite, so it's not going to give me anything better. The cost of S and 1 is going to be 0 using 10, so it's not going to change it, so it's going to be as the previous cost. This is going to be exactly that 10 cost that you had before. How about B? The cost of B, the only edge incoming to B is the node from E, but unfortunately the cost of E and 1 from the table, I know that this is going to be infinite, so it's not going to update it. So for B, we are going to still have infinite. How about C? The only incoming node for C again is from B. The cost of B and 1, this is infinite, so C is not going to be updated. D, the only incoming edge is coming from C. Already the cost of C and 1 using at most one edge is infinite, so the D is not going to be updated. How about E? For E, there is 3 incoming edge. One of them is coming from A. Okay, the one that's coming from D is infinite, this one is infinite, but the cost of A and 1 is 10. So yes, the cost of E can be updated to 12, right? 10 plus the cost of this edge, which is 2. So the cost for E, the cost of E and 2 has been updated to 12, and the parent for E will be updated to A. The other node that we have here is F. The incoming edges for F is only 1 edge that is coming from G. The cost of G and 1 is 8. So 8 plus 1, yes, the cost of F can be updated as well to be 9. And the parent for F will be updated to G. How about G? The only incoming edge for G is basically from S. So it's not going to update it. Definitely this is going to be as before, which is 8. So now we are done with filling the second column. Basically the third column, but the column number 2. Now let's actually just calculate the one more column here. This is showing you that how the parent column and how this table of D of V and I will be updated. Now we are going to actually update D of V and 3. So you see that the algorithm basically just fills the columns, all the table column by column from top to bottom. There is no actual difference in the putting the order here. So again, for S, the cost is going to be 0. For A, the only... Okay, so see that this is actually the nice thing about the algorithm. We are going to calculate the shortest path for A. There are 2 incoming edges for A. One of them is coming from S, so the cost of S and 2 plus 10, this is going to be 0 plus 10. This is going to be something exactly that you have before, but the other edge is this one. The cost of F so let's just rewrite it. D of F and 2, D of F and 2 is 9, okay? Plus the cost of this edge, which is negative 9 minus 4, this is going to be 5. Yes, I got a better path to A from S, which is actually basically going to be this path. So the cost of the distance for A will be updated, and the parent for A will be also updated. So the parent for A will be F. Okay, then for B, actually there was actually another one more edge coming from B, but anyway, A is not going to be updated through B because D of B and 2 was still infinite, right? So it's not going to actually help this one. But how about B? Can we update the cost, the distance of B? There is only one edge coming to B. This is coming from E, right? D of E and 2. This is 12. So 12 plus the cost of this edge minus 2. This is going to be 10. So yes, we updated the D of B and 3 to be 10. and the parent for that one will be actually updated as well. How about C? There is only one incoming edge to C. This is coming from B, but unfortunately D of B and 2, be careful when you are running this algorithm, you have to always use the previous column. Okay, I cannot use this cost. Later on in the next iteration, this will help me to update for C, but for now, I cannot update C. The cost of C is still going to be infinite because D of B and using 2 edges is infinite. Okay, so the distance from S to B using at most 2 edges is infinite. So the distance of S to C using 2 or 3 edges is going to be still infinite. How about D? Again, the cost, the only edge coming to D is 3. Is coming from C, and we know that already the shortest path from S to C using at most 2 edges is infinite. So this is not going to be updated as well. How about E? There are 3 edges coming to E. One of them is from D. This one we already know that it is infinite, so this one is not going to help. How about this one? From A, D of A and 2 is 10. 10 plus 12 plus 2, this is going to be 12. You already actually have it, so it's not going to update it through that one. How about the last edge here? D of F and 2 is 9 plus minus 1. This is going to be 8. So yes, we can update the D of E and 3 to be 8. And the parent of E will be updated to F as well. Okay, so basically it's telling me that this edge is going to be coming. How about F? The only edge, incoming edge to F is this one, which is coming from G. D of G and 2 is 8. 8 plus 1, this is going to be just like before, so this is still 9. The same for G. The only incoming edge is coming from S. So the cost of this one is going to be 8. So now we are done with filling the this column, the 4th column or the column number 3. So, okay, apparently I'm actually filling all of this. All of the columns, but let's actually go for it. So let's fill the 4th column. For filling the 4th column, again, S is going to be 0. A, the incoming edges are going to be this one, and this one. So through this one you get exactly 10. Through this one you are getting 5. And through this one you are getting infinite, because D of B and 3 is still, D of B and 3 is 10. 10 plus 1, it is going to be 11, so it's not going to update this one. How about B? The only incoming edge to B is through E. What is the D of E and 3? D of E and 3 has been updated. So it is actually a good news for B, because this one plus minus 2, D of B and 4 will be updated to 6. So this was 5 as before, but D of B and 4 will be updated to 6. And the reason is that the cost of D of E and 3 has been updated. This is 8. No, the cost of no, you can actually see the effect of negative edges. Okay, the parent is not going to be changed. This is still E. Okay, but the cost for B has been updated. How about C? D of C and 3 was infinite, but no, there is actually just one incoming edge. But because the cost of D and B and 3 has been updated to 10, be careful, I'm going to use this one. I cannot use this one now. In the next iteration, I will actually use the new value of distance of B. But no, I have to use this one. So the cost for D of C is going to be 10 plus 1. This is going to be 11. How about D? The cost of C and using 3 edges was infinite. So still for D it is going to be infinite. But in the next iteration it will be also updated. How about E? So E has 3 incoming edges. One from D, which is actually still infinite, so this one is not going to help me. One from F, that already actually it was 9. 9 minus 1, which is going to be 8. How about A? The edge that is coming from A, the cost of E and 3 has been updated to 5. This is 5, right? Plus 2. Yes, this is going to give me a better cost, 7 for E. So the distance for E is going to be updated to 7. And you have to update the parent for E as well to be A. Now you can actually see that now the path that we have found from S to E was basically actually this path. You see, using 4 edges. Basically, I have actually used the completely 4 edges. This is going to be that path. The only reason here is that we have actually negative edges. Otherwise, it was not possible. So how about F? The only incoming edge for F is coming from G. Basically, G hasn't been updated, and so it's going to be just like 9 as before. And also, the incoming edge for G is from S. So this is going to be just like before. It's not going to be updated. This was the 4th column. So now let's actually just see how to fill the 5th column. Again, for S, this is going to be 0. For A, there is an incoming edge from S, an incoming edge from F, an incoming edge from B. But B, D of B and 4 was 6. So plus 1. This is going to be 7, so A cannot be updated. It's just the previous value is going to be the minimum one. How about B? The only incoming edge for B is coming from E. The cost of E and 4 has been updated basically. It is now 7. So 7 minus 2, this is going to be 5. The cost for B is now updated. Okay, so the parent will be the same as before basically, but because the cost for E has been updated, the cost for F has been updated as well. The distance for F has B is going to, sorry, B, not F, has been updated as well. How about C? The only incoming edge for C is coming from B. D of B and 4 is already, it was actually 6. So 6 plus 1, this is going to be 7. This is better than 11. You update it to 7. How about D? The only incoming edge for D is from C, which the cost of C using 4 edges is going to be 11. Be careful, I'm not going to use this one. In the next iteration, you will use that one. So 11 plus 3, so the distance for D is going to be 14. And the parent of D has been updated to C. Okay, and then the distance for E, there are 3 incoming edges. So D of A and 4, it is 5, so it's not going to update anything to get you anything better. D of F and 4, it was still 9, so it's not going to give you anything better. D of D and 4, it was infinite, so it's not going to give you anything better for E. So still E is going to be 7. F, the only incoming edge is going to be from G. G hasn't been updated, so basically it's going to be just the same as before, and this one is going to be the same as before. So it shows you this part, and then for the sixth round, the sixth column, what would happen for S is going to be 0. For A, the incoming edges are coming from S, F, and B. B actually have been updated in the previous round, but still the cost of actually adding D of B and 5, this is going to be 5, right? 5 plus 1, this is going to be 6, so it's not going to change this one. For A is going to be 5, is still better. How about B? The cost of the only incoming edge is coming from E. D of E and 5 is 7. Minus 2, it's not going to actually give me anything better for B. So for B, it is still 5. How about C? This is coming from D of B and 5 plus 1. So for C, I can get actually the distance 6. How about D? For D, this is going to be the distance of C and 5, which was 7. 7 plus 3, so this is going to be 10. Okay. And what else? For E, the incoming edges are going to be from A, from F, and from D. D of D and 5 was 14. 14 minus 1, this is going to be 13. This is not better than what I had before, and the edge from A hasn't been updated, from F hasn't been updated, so this is going to be still 7. Again, for F, this is going to be the same as before. For G, this is going to be the same as before. I need one more round. You can see that I had 8 number of edges, and that's why the last column is 7. Okay, in the last column, still S is 0. A cannot be updated to get anything better. B cannot be updated basically because E hasn't been changed. C cannot be updated, but D will be updated. we can see that the cost of D is going to be the cost of C and 6, which is going to be 6 plus 3. For D, you get a better, the shorter path, 9. For E, it's not going to change anything. Basically, even 9 minus 1, it's not going to get you anything better here. For E, it is going to be still 7. For F, it is still 9. And for G, it is still 8. And that's it. This is the full actually table of the Bellman-Ford algorithm. And this parent table helps you to find the shortest path. For example, the shortest path from S to D will be basically this edge. The shortest path to reach to C is coming from B. The shortest path from S to B, it is coming from E, right? I'm actually just following these edges. For E, it is coming from A. For A, it is coming from F. For F, it is coming from G. And for G, it is coming from S. So it actually shows you the full tree of this single source shortest path, starting from S and visiting all these nodes. So the one more actually question about the Bellman-Ford algorithm is, what is the space complexity? Clearly, the space complexity using the algorithm that I wrote here, it is going to be n power 2, right? The number of columns is going to be n, the number of rows is going to be n, the number of edges is going to be n, so n power 2 is the table. But do I really need to keep all of these columns? You can see that whenever I was actually filling each column, you were just using the previous column. This one just using the previous column, this one just using the previous column. So basically, instead of just keeping the full two-dimensional array, you can just always keep just 2 columns. So instead of n power 2, you can just store it in 2 arrays of size n. So the cost will be, in that case, O of the cost of the space. The space complexity will be linear instead of n power 2. One more thing about the Bellman-Ford algorithm, which is very nice, and this is actually helps us to find the negative cycles, is that think about it, a graph that has a negative cycle. What would happen to the Bellman-Ford algorithm if there is a negative cycle? Basically, the question that I'm asking here is that here you can actually see the proof of the optimality, because the Bellman-Ford algorithm is dynamic programming. I'm going to just skip these proofs, but I would recommend you to read the full proof. But I think it is quite intuitive that why the dynamic programming algorithm finds the optimal answer. Basically, the reason is it checks all the possible paths. But that interesting property of the Bellman-Ford algorithm is, if you have a negative cycle in your graph, and if you run your algorithm for one more step, one more round, okay, so if you define one more actually column, if there is no negative cycle, the thing is, you would not get any difference between the last actually column, and this one basically the cost, because there is no negative cycle here. What you would get here will be exactly 0, 5, 5, 6, 9, 7, 9, and 8. If you run the algorithm for one more iteration of the outer loop, if you run it for, instead of n minus 1 step, if you run it for n steps, the last column that you will fill, there will be no difference between the column 8 and the column 7. So the step n and step n minus 1, there will be no changes. The reason is that when you are actually calculating when you run the algorithm for one more step, one more round of this loop, the outer loop, you are telling the algorithm to use n number of edges. If you use n number of edges to get from the node S to any node T, it means that you are actually just considering having a cycle in between as well. You are going to consider to use, if it is possible, you can use a cycle. But because there is no negative cycle, definitely your algorithm is not going to change, because it's not going to actually add anything else, right? Already it has found the optimal answer from S to T. And if there is no negative cycle, the answer between then in the last round is not going to change. So we can use this property to find the negative cycles in the graph. So basically the idea is that you can run the Bellman-Ford algorithm for one more step, and if you run the Bellman-Ford algorithm for one more step, you can, and if there is no difference, if you don't find any change in your table, it means that there is no negative cycle. But if you see some changes in the table, in that table of d of v and n, if there was any change between d of v and n minus 1 and d of n, if there was any change, if you get anything smaller in that additional round of running the algorithm, it means that there is a cycle, there is a negative cycle in your graph. But in this case, everything will be depending on the starting point. So the Bellman-Ford algorithm will find the negative cycles reachable from the starting point S that you run the algorithm over it. So maybe there is a negative cycle, but it is not reachable from S. How to fix that? The trick is we are going to, the trick is here, the solution is we are going to add, you have your full graph, okay? We are going to add a new node, let's just call it S, and add this node to all the nodes in your graph using the cost 0, okay? And then run the Bellman-Ford algorithm for n plus 1 steps. So basically the reason is that you have n number of nodes in your original graph, you have one additional node S, so n plus 1 nodes in total you have, right? Bellman-Ford algorithm runs for the number of edges minus 1, so in total you have to run it for exactly the equal to the number of nodes. This is going to be n plus 1 number of steps. If you run your Bellman-Ford algorithm for n plus 1 steps, starting from this new node S that has an edge to every node, if there is any cycle if there is any negative cycle in the graph, the algorithm tells you that it is reachable and you can find that path as well by just following wherever you find any node that in n plus 1 this is smaller than d of v and n. So basically there is a reachable cycle that v is over that cycle. I mean, at least v can be actually reached. I mean, the cycle is reachable from S through v. Okay, just by following the edges in the parent array starting from v, you can find the cycle. And the last thing about the Bellman-Ford algorithm is we can modify the Bellman-Ford algorithm. We can get some improvement and make it much faster if we just add some sanity check inside the loop. Whenever we stop changing d of v and I for any value of I and for any value of v, if for all the values of v, d of v and I is equal to d of v and I minus 1, if you didn't see any change in any step for all values of v, then you can stop. Basically, it just tells you that you are not going to get any better shortest path. I mean, using more number of edges, right? So you can stop your algorithm earlier. This is just, a modification over the algorithm. It's not going to change the time complexity, just depending on the graph. In some cases, you can stop earlier, and why not? We can definitely actually make your algorithm faster in practice.